Okay, so the next one, so this one we did, so checkpoints, yeah, these are similar. I think this one is easier, so you don't have that much problem here, I think. So theorem 2, that's also a very good one. In the book, this comes as an example, but this is because so ubiquitous in algebra. I want you to know at least the form of it. Okay, so the theorem, the reason that the name is conjugation and powers is because that expression in the pair of brackets is called a conjugate for A. But for the time being, you don't need to remember the name. So what I am telling is that if you are working in a group in this theorem, and then you have one group element which is sandwiched between two elements so that one of them is the inverse of the other one. So this combination. It doesn't matter if you have inverse here or if you have inverse here. You have a group element which is sandwiched between two elements, one inverse of the other. And then you want to raise it to power n. Again, when I talk about power n in group, I mean always an integer power. 0, positive integer, negative integer. This is a very nice one. It does not affect on these two. It will only have effect on the middle one. So it becomes e a to power n b inverse. Yes? Okay. The proof of this is not hard. You can do it mathematically. If n is 0, of course, the left-hand side is e. Why the right-hand side is e? Because a to power 0 is e, so e is here, and then b inverse is all again e. That's correct. If n is positive, you have to prove it using mathematical induction. Okay? But why do you expect that this should work? I don't want to write the proof here because we are a little bit behind today. So how should I, yes?
If you write them out.
Yeah, exactly. For example, let me write it 3 times. For example, B, A, but do it in a mathematical induction way. So if I want to do this, it means that I have to multiply this expression by itself how many times? 3 times. Yes? But then what you see, the combination is in a form that these two will be always canceling one another. So this B inverse and B becomes E. This B inverse with the next one becomes E. One B survives from the first one. One B inverse survives from the last one. And then you have E, A. And then this becomes A to power 3. B inverse, yes? But what about negative powers? Why? So this is also correct for negative powers or not? For example, if I have minus 3.
I should solve theorem.
Yeah, so you have to use the definition. If I have a group element to power negative, what was the definition? The definition was to take the inverse first, but raise it to power 3. Do you agree? But then this is the socks and shoes theorem. But it will start from this right side. So it becomes B inverse, which is B. This middle one inverse, and the last one inverse. Do you agree? And then to power 3. And then because this is a positive power, I can repeat it 3 times. So it becomes BA inverse, B inverse. And you don't need to put pair of brackets. BA inverse, B inverse. And then you have BA inverse, B inverse. Yes? And then what happens? Again, the same scenario. This one and that one is E. This one and that one is E. So B is survived from the first. B minus 1 is survived from the last. A minus 1 times A minus 1 times A minus 1 means A minus 1 to power 3. But we just learned that A minus 1 to power 3 can be written as A to power minus 3. And then I have B inverse. So you see that minus 3 just goes here. Okay? Well, the proof is not hard. So if you want to write formal proof, write it for 0 separately, write it for any positive integer and use mathematical induction to prove it, and exactly the same idea for negative integers. Yes, please.
No, the start is B. No.
Does it? Oh, that's correct.
I mean, I used to have a small.
No, but I want to say that whatever this n is,
Yeah, but we're going to prove it equal to B minus 1 A and B. No.
No, I understand. The reason is that I wrote it different here. Sorry, you're right. What I wrote in my notes is different from what I have written.
Oh,
Yes, but that's also correct. I told you, it doesn't matter. If B inverse is here, B is there, it works. If B is here, B inverse is there, it's also working. Sorry for that. Okay. But the idea is important. If you have an element which is sandwiched between two group elements, one inverse of the other, you just copy them in the same way. You just flip this n to the middle one. Yes? Yeah, sorry. This is not exactly the proof of what I have written. I understand the confusion. Because in my notes, I start from B inverse and then. Thank you very much for saying it. Okay, so let us go to the next one. Let us do this example together. This is not a hard one, by the way. Let x and y be elements of a group G such that this happens. Let me write it on the board. I have y minus 1x and then y. I know it is given to me x to the power of 5. I am asking this question from you. So how can I write y to the power of minus 2 x cubed y to the power of 2 in terms of x? This is the question mark. Yes? These are very, artificial examples. So we say that we have two group elements x and y. We know that it fits this equation. They fit in this equation. We want to find this only in terms of x. Okay, so what do you think we can do? I want to give you a little bit of time because you have to get used to this abstract way of thinking. This is an example for this theorem. Can you help me? What do you think I will do first? Look, what I want to have in the middle, you see, this is exactly the combination we are familiar with now. What I want to have this to power 3, okay? Because in the middle, what I want is x to power 3. So my advice to you is don't think to be able to see everything from the beginning. So you have to do some trial and error. So what do you think I will do now? I want to have this x to power 3 somehow in the middle. What should I do? You have this theorem at your disposal now. What should I do? I want to raise it to some appropriate power.
3.
3, yes, why don't you say? So x to power 5 to power 3. Okay, that's what I'm saying. Of course, it will not fix my problem exactly, but I'm getting closer to what I want. Okay, why I'm getting closer? Everyone should immediately tell me what is on the right side. X to power 5 to power 3. Definitely it is x to power 50. But according to what we learned here, what can I write for this one? This is one group element sandwiched between an element and its inverse, and the whole combination is raised to power 3. According to this theorem, this will not be affected, this will not be affected, so copy and paste them. But then this middle one will be raised to power 3. Do you consider this a progress or not? Is it a progress? Yes, because this expression that I have is a little bit closer to this expression because of the existence of x to power 3 in the middle. But the problem is, of course, not solved yet, because this combination that I have here is not exactly what I want. What I need is y to power 2 on the right, y to power minus 2 on the left. But what I have is y to the power of minus 1 on the left and 1 on the right. So what, yes?
You can left multiply with the inverse of y.
Very good, and
right with the other one.
good. So yeah, in the exam, you just need to write it. You don't need to write that many words. So you write this from the left, and you multiply y from the right. Yes? If you want, you can put these dots here. So it means that I am multiplying this equation from the left by y inverse, multiplying it by y over y. So do it in your head. So what happens to the left? The y inverse that I am multiplying from the left sits here. So let me write it one way, okay? But I have to do the same thing on the other side. Yes? Okay, let me go one more step. No one writes that because there is a better name for it, and that is y to power minus 2. Copy and paste x to power 3, and then y squared. But the problem is that this is exactly what I want, but I am still in trouble. Why? Because what I get is not in terms of x. It's a mixture of x and y again, which I don't want. So I have to find another way to fix it. So let us write it for the time being. So how do you think I will solve the problem now? Anyone else? Yes, please.
We can, the original, yeah, it's, if you do it 15 times with just, what is it? The thing that we did in the beginning.
Yeah, you don't need to, of course, in the exam, if you want to do
Yes,
it, be my guest. Use the theorems.
Yes.
Okay, so this one, I can write it as x to power minus 1, x, y to power 15. Yes, I am using the same theorem, but from this direction to that direction. Yes, is that everyone agrees that this expression I have written here is equal to this expression? Yes or no?
Yes.
Okay, but is it good or not now?
Yeah, it's good.
It's good. Why? Because this combination has a name from the very beginning.
Oh.
It's x to power 5. So this means that y inverse, y minus 2, x to the power of 3, y2 is x to power 5 to power 15. Yes? But what is x to power 5 to power 15 is just x to power 75. So I was able to do it. If you grant me this, I was able to show you that this expression that you want is x to power 75. And that is expressed in terms of x. Yes? So these are the examples you have. This needs a little bit different way of thinking. Yeah? So you have to develop this way of thinking. Any questions here? Understandable? Okay. So let us go to the next one. So this is checkpoint 2. It's very similar to this one. It's a little bit more tricky. So I will leave it for you. Okay? So now this is the very, very important lesson, and that is the lesson of subgroups. It's a very important topic, the notion of subgroups. So let us start with the definition of a subgroup. So let me do something on the board for you around the board for notes. So if you want to have an imagination, so let us say that this is my group G. So a group has two things, a set and a binary operation on the set. Okay? So this is the set of the group. If you choose one subset of your group, I will call it H. Okay? So this subset, this is the symbol that I use for subset. What's the mathematical definition of a subset? When I say H is a subset of G, means whatever is in H is also in G. This is a subset. Okay? And then, of course, I consider this not to be empty. So we want to see what is the meaning of H being a subgroup. So here H is a subset. Okay? So you already know what is the meaning of a subset. But now I want to say that H is a subgroup. For subgroup, we use this symbol. Okay? So this means a subgroup. So what do I mean that H is a subgroup? It means H, with the binary operation for G, itself is a group. That's the meaning of a subgroup. Yes? Did you follow? A subset of G, which is not empty, is not necessarily what we are going to call a subgroup. A subgroup is a part of the bigger group, so that that part itself, under the same operation of G, is a group again. Yes? If that is the case, we say that H is a subgroup of G, and we symbolize it using this notation. Yes?
Maybe a stupid question, but G is a set, the group must include the operation, but I assume it's just simplified way called group.
May you repeat it again?
A group must include the set G, but also a operation. operation. But now we are calling group G instead of parenthesis G star. As a,
I have written itself a group under the operation of G. So in principle you are right, but I don't want to repeat all of this.
Sure, yeah.
So it means that if you want, I can write it in this way. I have a group like this, and I pick an H from G, and then the same operation here. If H with the same binary operation is still a group, I call this with respect to this a subgroup. But every time I will not write these notations because it becomes clumsy. That's the only thing, but you are 100% right. Okay? So that's the sub, so is that clear? So might be that's a good way. So it means that when I say I have a G, I have a group, it means that I have a set and a binary operation on that set. If I pick a part of it, a subset of it, and then accidentally or by some reason, that subset becomes again a group with the same binary operation, then we call H a subgroup of this group. Is that right? Okay. Okay, now we want to have a theorem to see when a subset is also a subgroup. Okay? Of course, you don't need a theorem because you can check the axioms of a group every time for H. But this is not a very efficient way. We want to have a theorem. But let me continue a little bit more. So, can you guess what is the smallest possible subgroup of a group? For example, I give you a group G, and I ask you what is the smallest subgroup that G can have? Yes? The set consisting of only the identity element. It's very simple to see that this is a group itself. And what is the largest one? G itself. So that is the largest subgroup, and this is the smallest subgroup. These two subgroups are called trivial subgroups. Okay? Every subgroup, if there is another subgroup, which is not this one and that one, is called a proper subgroup. And if you have a proper subgroup, you usually denote it by this symbol. So if you use this one, it means that you consider the chance that H is equal to G itself. But when you see this notation, it means that H is a subgroup, but it is not G itself. So these are just simple notations. So in principle, you don't need any theorem for a sub to test if a subset is a subgroup or not, because you can check all the axioms of groups for H. Okay? But I want you to know this theorem, which is a very nice theorem. Theorem number 3, two-step subgroup test. Let G be a group and let H be a non-empty subset of G. If A, B is in H whenever A and B are in H, and A inverse is in H whenever A is in H, then H is a subgroup of G. Okay, so let me explain it here for you. So this means that if you pick one part of your group which is not empty, okay, so let me write like this. H is not empty. H is closed under multiplication, under the binary operation. And if H is closed under taking inverses, then from these three conditions, you can conclude that H is a subgroup of G. This is what we want to show. Yes? So it means that H is closed under binary operation, H is closed under taking inverses, and H is not empty. These three conditions together, it's called two-step because usually this is in the definition itself. That's why we check two conditions. Closeness under binary operation and closeness under taking inverses. We want to show that these three these two in principle are enough to conclude that H is a subgroup of G. Why is that? We have to check. We have to check the conditions of subgroup for H. The first condition is, of course, this operation should also be a binary operation on H. And this is guaranteed here. So the closure is guaranteed by this assumption itself. The second one is associativity. Why do you think the associativity doesn't matter here that much? It means that for every A, B, and C in H, why do you think that A, B, C is equal to A, B, C? Yes?
Because it needs to be true for G to be a group.
Yes, because all elements coming from G enjoy this property. Yes, when I choose 3 elements from H, they are automatically in G as well. So they will also automatically enjoy this. So it means that the subgroup H inherits the associativity from the mother group. Something like this we say in algebra. Yes? Okay, so that is also, we don't need to check. What else we need to check? Existence of the identity element. Okay, we have to confirm, because you know that I know identity element is in G, but there is no guarantee that identity element is in H. I want to convince you that under these two conditions, identity element will be in H as well. But can you see how?
Suppose inverse and A are in the group, and A inverse times A
Is in a group. But we need this assumption now. Yes? Because H is not empty. This means that there exists H in H. Yes? Because H is not empty, so that is needed for this exact part. At least there is one element in H. Okay? So now, if H is H, according to the closeness under inverse, I can guarantee you that H inverse is also in H. Yes? And now what do I have? I have H in H. I have H inverse in H. But I have closeness under a binary operation. So this means that H inverse belongs to H. Yes? But what is H inverse? Is just E. So this means that E also belongs to H. And I need to show that you need an inverse, but the inverse is already one of the parts here. These kinds of proofs, I want you to feel that what we are doing is needed. Do you feel it or not? Yes? Okay. So this means that from now on, if I give you a subset, and I ask you to prove this subset is a subgroup, you need to check that your subset is not empty. You need to check that your subset is closed under the binary operation. You also need to check that your subset is closed under taking inverses. And my recommendation is for first part, check the identity element. Because you want to show it is not empty, so you have to convince me that there is something in it. The simplest thing to check is the identity itself. Is that right? But you need an example, I know, but let me give you the example. Yes, please.
Just a quick notation question.
Yes.
You said about trivial subgroups, that
Yes.
includes the subgroup with just the identity element as well.
Yes.
If we know that it's not the full group, but
Yes.
we don't know if it might be just the group with only the identity element. Do we still write it as strictly less than, or is it?
Yes.
Okay.
If G itself is not from the beginning containing one.
Yeah, so it's only if the full group
Yeah.
might be, then
Yes.
it's the first
Yes.
position. Okay,
Yeah.
perfect.
Okay, so this is a very good example. Let me show you. Let G be an abelian group with identity E. Show that this set H is a subgroup of G. So I want you to see how we should write these projects. So here, G is an abelian group. Abelian group. And then I am defining for you a set H in this way. The set consisting of all x's in G such that x squared is E. By the way, I don't say that what is E. E is always the identity element, okay, of the main group. So let us get a feeling about this. So it means that I have a G here. It has some elements in it. I can square these elements. Some of these elements, when I square them, they become equal to E. Some of them might not become equal to E. I will only choose those part of elements so that squares are equal to E. So it is clear that it will be a subset of the whole set. I want to show that this one is a subgroup. Is that understandable? So this G has different elements. I take one of them, raise it to power 2 to see if it is E or not. If it is not E, I throw it out. If it is E, I put it in my bag. And I do it for all elements. At the end of the day, I get a collection of elements in this smaller bag. My question is that, my claim is that this smaller bag is a subgroup of the original group. If the original group is, of course, abelian. So let us do these tricks. The first thing you have to do is to convince me that this H is not empty. And I just told you that for making that part, it is always better to make sure that E is there. Okay, is E there? Why? Do you agree with this sentence I am writing? E belongs to G, and this symbol means and. E to power 2 is also E. Do you agree? So, in order an element to get visa for H, it has to have two conditions. It should belong to G, and its square should be E. So E belongs to G, and its square is E. So can I conclude that E belongs to H? Yes. So this means H is not empty. Is that okay? Okay. Now this is the first part. What should I do for the second part? Closeness under taking inverses. What does it mean? It means that if H1 is in H and if H2 is in H, I have to convince you that H1, H2 belongs to H. Yes? Okay, so let me start. In order to show that this belongs to H, what should I show you? I need to show you that this belongs to G and its square is E. In order to show you. By the way, this is not a good thing because usually people start with assumptions. This is not a good strategy in mathematics. Do not start manipulating your assumption because you don't know what you need now. You know this is your goal. Usually start from your goal and to see where you need your assumptions. Okay? So if I want to show that H1, H2 belongs to H, forget about this one. My goal is to show this. I ask myself, how should I show this? There is one answer to it. I should show you that this has the property of the elements of H. What are the properties? They belong to G, which is the trivial part, because if H1 and H2 belongs to H, they also belongs to G, so the product is also in G. One more thing which is not trivial, I have to convince myself. We show that H1, H2 belongs to G, and, can you complete it for me? And what?
H1, H2.
H1, H2 to power 2 is E. Do you agree? I want to show that H1, H2 belongs to this set. I should show that this convinces these two conditions. But this one is trivial. Yes. Because H1 and H2 are in G, definitely the product is in G. But this one I have to convince you. So H1, H2 to the power of 2. Can I write it H1 squared, H2 squared? Yes or no?
Yeah.
Why?
It's
It's abelian. If it was not abelian, I was not able to use that. So it's okay to write it. So mention it in the exam. G is abelian. Okay, but now, can I write this one as E?
Yes.
Why? Because H1 belongs to H. And H2 also belongs to H. So H1 to the power of 2 is E, H2 to the power of 2 is E, and the product is E. So that one is also done now. What about the third one? So the third one is that if H belongs to H, I have to convince you that H inverse also belongs to H. Okay, how should I prove this again? Don't manipulate your assumption. Start from what you want to prove. How should we prove that? We have to convince ourselves that H inverse is in G, which is of course true. Yes, because if H belongs to H, H also belongs to G, so H inverse belongs to G. So that's great. I have to show that H inverse to power 2 is equal to E. But do you remember we learned this today? We can swap them. Yes, so I can write it as H2 to the power of minus 1. But what is H2? Because H belongs to E, H2 is what? H2 is E. And I have E inverse, but E inverse is again, is that right? So the subgroup is very, very simple to test. Clear? Okay. So the next one is a checkpoint, very, very similar to this one. You can do it yourself. And now let us go to this example, do it together. So let G be a group. Show that this set is a subgroup of G. Moreover, show that G is abelian if and only if this set is equal to G itself. And then this is a famous subgroup, but you don't need to be worried about these names. If in case you want to know, this subgroup is called the center of G. Okay, so let us go back to. So I give you a group G, not necessarily abelian here, and then I define a set for you, Z of G. This is the German word for center. I don't remember what that is. Okay, this is defined in this way. All elements in G such that AX is equal to XA for all AX in G. So can you describe what is the meaning of this subset? So try to imagine it, because you should also be very good in reading mathematical notations. So this is my group G. So I take one element from here. How should I see that if this element goes to this set or not? In other words, how should I know that I should keep this element or should I throw it out? So how should I know that? Can you just tell me in a very clear way, not just by notations? So for example, you take an element here. You want to see if this element goes within this new smaller bag or you have to throw it out. How do you understand that? In English words, yes?
If it's commutative over the binary operation.
No. Commutative is different from this. That's what I want you to see.
Oh, sorry.
Commutative means this relation holds for any pair of elements in the group. That is why the second part of the problem tells you that if that is abelian, this is nothing except the group itself. So your intuition is correct, but that is not necessarily the case if G is not abelian. So my question again, I have a G, I pick one element from G, I want to check if G is allowed to go to Z or it is not allowed to go to Z. How should I check that? I want you to be able to read the mathematical symbols. I take this A, anyone? I take this A and, yes?
Pick another element, the left multiply and the right multiply, check if it's the equation holds and check to the same check
For everyone. You see, it means that this A is fixed now. I check this A with this one to see if it commutes. I check this A with itself, of course with itself it will commute. I will check with this one, I will check with this one. If this one commutes with everyone, then A is allowed to go to to Z. Otherwise, I throw it out. Is that understandable? So that is the meaning of this center. The center is a collection of all group elements which commute with every element in the group. It doesn't mean the whole group is abelian. Is that right? Understandable? Okay. So that is the meaning you have to, when you see this, you should be able to understand it in this way, otherwise it would be hard. Okay, now I want to show you that this new collection is definitely a subgroup of G. There are three things I have to consider. I have to convince you that this is not empty. Okay, so, and I told you, what is the best way to see if it is not empty? To check that if the identity element is there. Do you think identity element is there? Why is that? Because first of all, identity element is in G, and for all x in my G, identity element commutes with every element, yes? And I don't need to write the answer, that's enough. Don't write more. So because of these two, I can conclude that E belongs to Z of G, so this means Z of G is not empty. Yes? And now the second one. I need to convince you it is closed under binary operation. So what does it mean? It means, for example, I take A and B in, so let me just write it. I take A in Z, I take B in Z, and I want to convince myself that AB is in Z. This is what I want to confirm. Okay, again, I want you to develop this habit. Don't start manipulating the assumptions. Start from what you want to show and to see where you need your assumptions. Then bring them in. Okay? Okay, so my target is this one. I want to show that AB belongs to Z of G. How do you prove it? You want to show that something is allowed to go to G. What you need to show me? Say it in English. I want to show that AB belongs to. I want to show that AB is allowed to go to Z. How should I show it? I should show that AB, say, commutes with every element of G. So you should be able to read this in English. Mathematical symbols are good, but you have to understand what is behind, what is the message behind mathematical symbols. So my goal is to show that AB belongs to this Z. I have to convince myself AB has the property of the inhabitants of this set, meaning that I have to show that AB commutes with every element of G. But you want to write it in the exam. How do you write it? I would say let what? Let X be in G. This means, by the way, let X be an arbitrary element in G. You don't need to write the word arbitrary. If you are a mathematician, when you read this, it means arbitrary is implicitly assumed. Let this be. We show that. I'm waiting for you. We show that. We show that. We show that what? Everyone. AB, please don't hesitate. You see, because if you, yes?
Equal to XAB.
Yes, do you agree that this is my goal?
Yes, yeah.
Yes, so please say it. Okay, so how should I prove it? I start from the left-hand side. But this one, you have to write all the details. Now, I want a volunteer. What is the next step? I want to show this. This is the question mark. I start from the left-hand side of my question mark. What is the first step? What? Associativity. Yes, I would write ABX. Yes? What is the next step? No, the reason I am waiting, because if you don't develop this skill here, the algebra becomes harder and harder. Okay? So you have to find a way to connect to this way of reasoning. The problems that I solved before, you have to be creative and skillful. These problems doesn't need any skills. Okay? You just need to read and understand what you are talking, because you see that this is minimal. My goal is to prove this. Then what I do, I use associativity. You might say, Bob, like, why associativity is useful, but it is not hard to see. Because when you do that, B and X will be next to one another. Yes? And then I know B is coming from Z. So I know B and X will commute. So that's the intuition behind that. Yes? So let us continue. So can I write XB here? Do you buy it from me? Why? But in the exam, say why. Why is that? Because B belongs to Z. Let me write 0. That is enough for me in exam. It means that you really understand what you are doing. You don't need to write too much. Okay? And then, what do you think I will do now? Associativity again. See, you are developing this feeling. Okay, this is not it has nothing to do with creativity. The nature of this problem is different from the other ones. Okay, so this becomes AXB. Why this was useful? Because now, can I commute these two?
Yep.
For the same reason. What was the reason? Similar reason. Yes? So it means that I can commute these two. So it becomes XAB. Yes? But what is the next step? Associativity again. Yes? Very beautiful subject, algebra. You enjoy it?
Yes.
Yeah, I'm excited. I have done it many times, but I enjoy it. So this is finished. So, and by the way, it's better to write left-hand side equals to right-hand side. Yes? Again, I am saying that some of the problems are extremely hard and creative. For the exam, if I want to give you some of these questions in the exam for the last parts, I provide you with the hints. There is nothing I can expect you just come up with the ideas out of the blue. But these things you can learn. These are not hard. Okay, let us repeat this. Is it finished or not? I have to do one more thing. Non-empty, we did it. Close under binary operation, we did it. Close under inverse, we have to do it. So now what we should do, number 3, I would say that let A belongs to Z of G. I want to convince myself that A inverse belongs to ZG. Okay? Agree? Okay, so again, write some sentence like this, but I want you to write it for me. So what do you think I would say? I would say let what? What should I say? I want to say that A inverse belongs to Z of G. I have to show that A inverse has the property of the elements of Z of G. In other words, I have to convince myself that this what? Commutes with every element in G. So I would say let, I don't know, you can change the letter. Y belongs to G. Yes? We show that, help me, what should I write? We show that what? Say so.
A inverse.
A inverse Y is Y. A inverse. Yes. I'm sure you know that, okay? But don't hesitate to say. You save my breath, okay? By the way, today is Iranian New Year, and it is at 3:45, so I have to run to my family, okay? So, yeah, help me at least. Okay? I can save some breath for the New Year. So, and then I want to show that. Okay, tell me, how should I start? I have to sacrifice my New Year, okay? I will stay here, you don't say. So, tell me. How should I start? I want to start and get this right. Yeah? No, you don't multiply by A. You know why that's not? Unless you know that this should be reversible. Because you are very sensitive to being reversible or not. But when it comes to your 10, you use it. Yes. If you multiply this, of course, you can get something correct at the end, but you have to make confirm that everything you did is reversible. Because this is what we want to prove. You don't have it. So don't do it. It's not a good way to do it. Because this is simple. Those methods are good to discover how to go forward. And then when you discover it, I would prefer to write it the other way around. Yes? You can start from here. If you want to change it, I would say that, okay, let me do it in this way. Now I use my assumption. I would say that now I am changing my strategy a little bit, even though the previous strategy will work as well. Find it yourself. But I can change a little bit my strategy. I would say that now my assumption is this is in Z, yes? So what can I conclude from here? The Y is chosen from G. A, by my assumption, is in Z. So what I can conclude that AY is equal to YA. This is different. You see, this one is something still I don't know, but this is something I know. So I can multiply it by whatever you like to. So then I multiply everything by A inverse from the left, yes, and by what? A inverse from the right as well. Yes? Then what happens? It becomes A inverse AY, A inverse is equal to A inverse YA, A inverse. Okay? But then, can you see that? Let us do it quickly. This A inverse A will be associative, so that becomes E. This becomes YA inverse. Yes? And then this one, A and A inverse associativity cancel out. A inverse Y is left. Yes? So here, my strategy here was a little bit different from here. Here, I started directly from the left-hand side of what I want to prove, and I reached to the right-hand side. And here, I didn't start from what I want to prove. I started from my assumption suddenly, and this is correct, and then I multiply them and then continue to simplify. Any questions? Understandable? Okay. So now the next one, by the way, we haven't finished the problem yet. We want to show that G is abelian if and only if the center of G is equal to G itself. On intuitive level, I hope that you agree with it. Yes? Because if it is abelian, it means that every group element commutes with everything else. So we feel that the center should be as big of the group itself. But that is not a proof. I want you to go home, at least for the weekend, okay? You can sit down and actually do it. The best thing people can do on weekend is doing mathematics, isn't it? So yeah, just go do that. Okay? So, but I want you to write it formally. Okay? And might be I also write it for you and then upload it on Canvas to see that if you want to write things precisely in mathematical form, how you should write it. Because in the exam, you have to write it somehow. Okay? And then the next one is a very similar one, not the center, but what is called centralizer. So you can also check that one. Yeah. I think subgroups are finished. Okay? I was expecting to go a little bit forward, but we couldn't. Okay, but somehow we have to speed up a little bit. Any questions? No? Thank you very much. Have a nice weekend, by the way.